Today, we'll take a look at how Neo4j Aura Graph Analytics powers predictive maintenance, catching costly failures before they have a chance to shut down the production line. A single machine failure on a production line can cost a company over $100,000 per hour. Luckily, we can use Graph Analytics to answer questions like, which machines are most likely to fail soon? Which machines sit on critical paths that glue the line together? And if a bridge machine fails, what's our quickest reroute? While traditional relational models struggle with those intertwined paths, a graph model solves these problems in seconds. We are going to represent a mock production line using nodes for each machine and edges to represent how they are connected. From here, we can simply project the data we want to analyze, run some algorithms, and then finally act upon the results. Plus, this can be done with Aura Graph Analytics, a pay-as-you-go serverless offering from Neo4j that runs up to 2 times as fast as open source competitors. The first thing we're going to do is spin up a serverless Graph Analytics session that only exists when we need it. Today, we will be using data from AuraDB, but Graph Analytics supports any enterprise data that can write to a pandas data frame. Next, we can pick from any of the Neo4j Graph Analytics algorithms. Then the results can be written back straight to AuraDB, where dashboards and applications can read them in real time. Finally, we can close the session. The compute disappears, billing stops, and storage stays online for the next time. Before we dive into the demo notebook, I wanted to take a moment to talk about the Betweenness Centrality algorithm. Betweenness counts how often a machine lies on the shortest path between a pair of machines. This algorithm reveals hidden bottlenecks that simple volume or degree counts miss. So for each pair of machines, we identify the shortest path between the 2 machines. Then a machine earns a point if it falls on the shortest path between 2 pairs. Finally, we add up the points for each machine to get its betweenness score. A high score machine is a bridge. Its failure breaks 2 whole sections apart. A low score machine has alternate routes, so its failure stays local. So quickly, we have 4 steps: enumerate pairs, identify and list shortest paths, generate credits for nodes on shortest paths, and sum the credits for each node. We're going to go through this on a toy example by hand, also known as on this computer. So here we have a simple graph. The first thing we're going to do is enumerate the pair of nodes. Now this is a directional graph, and so you'll notice that we don't have A to B because A goes to C, but C does not go to B. So there is no path between A and B for this directional graph. Now that we've identified all the potential paths on this graph, we then identify the shortest paths. Note that for many of these paths, there's only one option. For example, the shortest path between A and D can only be A, C, D. There is no other alternative. However, to go from A to F, there are 2 potential paths. You could either go A, C, D, F, or A, C, E, F. For the purposes of betweenness, we want to know each of these paths. Next, we generate the credits for the nodes on each shortest path. And in the case that there are 2 options for shortest path, we'll have to calculate those specifically. So here you can see no nodes actually fall between A and C, so nothing gets points. Here C gets a point because it falls between A and D. And then this is where we have to start giving partial credits. So D falls in one of the 2 shortest paths, so it gets half a point, and E falls in between one of 2 shortest paths, so it also gets half a point. Once we calculate each of these points, we can then sum them up. So A gets 0. It does not fall between any shortest path because it's the beginning of the line. B and F also get 0. They're all at terminals. C is our highest betweenness score with a score of 6, and then D and E both get 1.5. Remember, the 0.5 comes from there being multiple ways to get from one place to another. So to recap, we first enumerate the pairs, list shortest paths, add credits between nodes, and sum each node. However, doing this calculation for a very large graph doesn't make much computational sense. So the graph analytics implementation is based off of Brande's approximation algorithm for unweighted graphs, allowing more efficiency with large graphs by sampling nodes and only calculating a certain percentage of them. And with that, let's jump into the notebook. Everything here has already been executed. We're simply going to scroll through, talk about some of the code, and interpret some of the results. The first thing you need to do is make sure that you have installed and imported all your dependencies. This includes the Neo4j Graph Analytics library, which we will use to set up our session. After that, you need to make sure to have your Neo4j AuraDB credentials for authentication. If you're working in Colab, I strongly recommend storing those keys in Google Secrets, as hard coding them can be a bit of a headache sometimes. After that, we are ready to start a session. To start a session, you will have to estimate your node and relationship count. In our data set, we have only 20 nodes and about 25-30 relationships, so we can keep this relatively small. Again, these counts can be estimates, but make sure they're not wildly too big or too small for the data that you plan to use. And then once your session is created, the billing begins. The first thing we'll want to do is create a graph projection. Here, we are projecting all of our machines and their relationships into a single in-memory graph called full. Building this one consistent projection ensures that every algorithm runs against the same structure. The first algorithm we'll run is weakly connected components. For our data, we want a single connected component. If there were multiple components, that would mean you would have multiple separate production networks. But here, we want to make sure that every single part is connected. And we can see the results saying that there is one component with 20 machines in it, exactly what you wanted. Strongly connected components is a way that you can look for loops, recycling paths, or cyclical flows that can slow down productivity or imply wasted capacity. We have included a few small cycles intentionally in this data. You can see here that 5 and 6 are both in the same component, implying that they are highly related. And then 8 and 9 are also in the same component, implying that they are highly related. If we go ahead and look at those nodes, we can see that they form actual loops here. Next, we have criticality analysis. We'll start with PageRank Centrality. PageRank Centrality was initially designed to rank web pages. It measures a node's importance by both the quality and quantity of incoming edges. So for A edge B, it means machine A feeds into machine B. A high PageRank score indicates that a machine receives material from many other well-connected machines. If we look at our chart, you might notice that machine 20 has a lot of connections going towards it. So we would expect this to have the highest PageRank. And in fact, it does. Closely followed by machine 19. Let's take a look at that. Here we see that machine 19 also has multiple inputs and is then connected to the very important number 20. Additionally, we can assume that these chains are producing a lot of throughput into our assembler. And now we get to the algorithm we previously discussed, Betweenness Centrality. Well, the previous algorithm, PageRank, highlighted the machine with the most influence based on incoming flow. It didn't capture the machines that sit between the major areas of workflow. Betweenness Centrality fills this gap by identifying machines that appear frequently on the shortest path between others, often acting as bridges and also single points of failure. Machine with the highest scores connect upstream and downstream sections of the plant. In the results, machine 3 ranks high, But it's not because it handles the most volume, but because it links up multiple parts of the workflow. If it goes down, it risks disrupting connections across the system. Let's take a look. Here you can see 3 is located here. While it may not have as many connections or inputs as 20, it is on the path between so many different pairs of nodes. Similarly, 13, 14, and 15 rank highly. It might be initially confusing why these might rank higher than some other nodes, but it's because we're counting both from 1 to 15 and from 13 to 20. So those points add up. So we can see that nodes such as 14, 13, 3, and 15 act as structural bridges in the workflow. Their high scores suggest that they connect otherwise separate paths, making them key points of potential disruption if taken offline. The final analysis in this demo is a similarity analysis. Here we use FastRP to embed each machine into a 16-dimensional vector, and then use k-nearest neighbors to show which machines are structural twins. Now, FastRP vectors are built here by sampling the graph around each node, so 2 machines with similar surroundings will end up with similar embeddings. This does not mean that the machines do the same job, just that the structures around them are similar. Creating the embeddings is very simple. You can see we just call this function, let them know how many dimensions, and where to write the properties. You can see some examples of embeddings here. Then we need to create an additional projection because our original projection does not include the embedding properties that we just created. Once we've created this embeddings projection, then we can run k-nearest neighbors on the embeddings. Finally, we close the session. At this point, compute evaporates, the link stops, and the data is written back to its source, ready for any dashboard or downstream process. So in this demo, we've seen how we can use strongly connected components to identify areas that include loops that might suggest there is some inefficiencies. We also used PageRank to surface the busiest hubs, and we use Betweenness Centrality to spot machines whose failure would be disruptive, even if they aren't the busiest machines. And note that these predictive maintenance insights pop out of a simple graph production. No heavy ETL, no idle hardware, just answers. Thanks.